Well, hello and welcome to the 7th lecture of this short course called Behavioral Theory of Systems with a View Towards Data-Driven Control. So, in the last lecture, we looked at this very interesting process of doing row operations which are very similar to the kind of row operations that we do in linear algebra, but a little different. But here, because here we are dealing with polynomials as opposed to just constant numbers. But even then, because of Bezu-Aryabhatta identity, it is possible that through these row operations, elementary, which we call unimodular row operations, because the matrices that encode these row operations have to be unimodular matrices. With these unimodular row operations, we can convert a given system of ordinary differential equations or ordinary difference equations, linear of course, with constant coefficients, into a system of equations which is upper triangular. Right? I actually described the whole method algorithmically, so that step by step, if we follow that process, we can obtain that special form of the system of equations. I feel it would be worthwhile if we go through a small example, a toy example, and see how this process is actually done. Many of these processes will be there in your exercise problems, which if you solve, you'll get the idea much better. Okay? But let us first do this toy example. So we are going to look at this polynomial matrix. I'm going to look at a 3 by 3 polynomial matrix, xi plus 1, xi plus 2, and xi plus 3. I'm going to keep it very simple. Xi plus 4, xi plus 5, and xi plus 6, xi plus 7, xi plus 8, xi plus 9. That's my system. And I'm sure you can appreciate the fact that if you are trying to find out the kernel of this, you're actually solving a 3 by 3 system of ordinary differential equations with constant coefficients. Linear ordinary differential equations with constant coefficients wouldn't be easy. I mean, how do you solve for simultaneously these 3 equations? You cannot solve this separately. Separately you can easily, because you can look at in fact, if you want to solve it separately, you have xi plus 1 times w1 plus xi plus 2 times w2 plus xi plus 3 times w3 equal to 0. Like in the case of linear equations, you can take w2 and w3 to be arbitrary C infinity functions, and then w1 is given by xi plus 2, xi plus 1. You see, this is only representational. This ratio doesn't really make sense as of now to us. Xi plus 3, xi plus 1, w3. You can take this as a transfer function, and use Laplace transforms to find out a solution w1. But that for this equation separately, standalone. I want to solve all the, you see, having this system of equations w1, w2, and w3 equal to 0, having this system of equations, it means that I have to solve them simultaneously. That is, w1, w2, w3 must satisfy not just equation 1, but equation 1, equation 2, equation 3, all 3 of them simultaneously. How do you solve them? Yeah, not easy, right? So what do we do in this situation? That's what we are going to learn now. Okay? Now see. Okay. So we have xi plus 1, xi plus 2, and xi plus 3. All right. I have here xi plus 4, xi plus 5, and xi plus 6. Then I have xi plus 7, xi plus 8 and xi plus 9. I want to solve this, but I want to do this row operation and bring it to a form which will be upper triangular. And if it is upper triangular, it will be much easier to solve, as we will see very soon. Okay. Now, what do we do in this case? Remember, I take this guy. All of them, I just scan through the first column and find out the guy which has the least degree, and then I take that guy to the top through a permutation of rows. Permutation of rows, of course, is a unimodular row operation, so that's okay. But here I don't need to do that because every element in the first column has degree 1, right? So I look at the first guy, and I use this guy to do Euclidean division with remainder with this guy. Yeah, I can do that one by one, but for the sake of saving time, I'm going to do this simultaneously. I'm going to do this row operation on row number 2, row number 3 simultaneously. What is the result of that? The result of that, of course, is that the first row remains intact as it is. The second row changes by what? The second row changes by second row minus 1 times the first row. Okay? If we do that, then we have xi plus 4 minus xi minus 1. That's 4 minus 1, 3. Okay? Then this will be xi plus 5 minus xi plus 2. That will be 5 minus 2, 3. And this guy will once again turn out to be 3. Okay? Likewise, if I do this subtraction, I'm going to get xi plus 1 minus xi plus 7 minus xi plus 1. That is 7 minus 1, 6. Right? Likewise, this will also be 6, and this will also be 6. Okay? How have I obtained this? Remember, I just did row operation. So multiplication by 1, 0, 0 remains here. This is minus 1, 1, 0. This is minus 1, 0, 1. Right? This is the unimodular row operation that I did. Now you see, it's very simple now. Once again, I will just do another row operation. Okay? And I will look at the guy with the least degree. But you see, I can, it's actually not required, let it be like this. So I can bring the guy with the least degree, right, to the top. So by a permutation of this kind, 0, 1, 0, 1, 0, 0, 0, 0, 1, this is the permutation matrix that I can make this guy act on this matrix, and that will produce 3, 3, 3, xi plus 1, xi plus 2, xi plus 3, and 6, 6, 6. Okay? Now what do I do? Once again, I just do row operations, right? I do row operations by this guy. I divide this guy by this one, right? But you can see this is now very simple because this is just 3, which is a constant. I can just divide, I can just multiply this guy by xi plus 1 divided by 3, right? Xi plus 1 over 3, multiply this row by that, and subtract from here. What is the result of that? Okay, of course, the first row remains intact. The second row changes by, the second row is minus xi plus 1 by 3 multiplied to row 1. That is, this will become 0. This will become xi plus 2. Let me just write it here. I will delete it. Xi plus 2 minus xi plus 1 divided by 3 multiplied to 3. That is just xi plus 1. So this is xi plus 2 minus xi plus 1. The result is just 1. Okay? The result here will be 2. is I plus 3, right? I think I'm okay. This is the result is just 2. So you see I have obtained this. I will simultaneously divide this guy also, but this is very simple now, and just multiply by 2 and subtract, and the result is just 0, 0, 0. Okay. So what have we done here? The first row remains of course intact. The second row is changed by minus xi plus 1 over 3, 1, 0, and this is just minus 2, 0, 1. This is a unimodular row operation, and I have this form. Okay? Is that okay? And you see, I just we are done. This is already upper triangular form because these guys have already obtained 0. This is coincidental, and I did not want to make this guy 0. This just became to be 0. So now I realize that this system of equations is actually equivalent to this system of equations. Yeah, this system of equations, because I have come from this matrix to this matrix by a series of unimodular row operations. Now this is surprising, right? Because this looked like a differential equation. In fact, this is a system of differential equations. It turns out that actually it is equivalent to a system of just linear equations. Okay, right? I hope you have you see the point how it goes, right? There will be more such. This was very simple, as I have already conceded. This is a simple toy example. It's very easy to do these processes by hand. But there will be more complicated systems, and ideally one should write a computer program which can take care of these sort of operations, this sort of unimodular row operations. But the point is that the point is that through this unimodular row operations, you can change a given polynomial matrix into this upper triangular polynomial matrix form, right? Nowhere have we made something like row operations which are not allowed over this ring. That's the crucial bit. You see, what is the crucial difference between let's say a Gaussian elimination kind of row operation and the row operation that we are doing here based on Euclidean division algorithm? The point is that nowhere have we divided by polynomials. Everywhere we are doing only multiplication and addition and subtraction. So 3 operations: multiplication, addition and subtraction. Nowhere have we done division by non-constant polynomials. You can divide by real numbers, non-zero real numbers, but not by polynomials, because in general division by polynomials over the ring of polynomials doesn't make sense. Correct? Yeah, we do not remain confined within the realm of these differential equations if we do division by polynomials. Division by polynomials tantamounts to division by differential operators, which is nonsensical, right? That is why this is so important to understand that in this row operations, these unimodular row operations business, we are never going out of the realm of differential equations. Although we are using this weird looking, tadpole looking Greek letter called xi, it's spelled as xi, xi, but actually it is a placeholder for the differential operator ddt. Okay. So don't forget that. That's why we are not allowed to go beyond the realm of the polynomial ring. That's why it is important to note that all these operations are allowed in the confines of this differential operators, in this differential equations business. Okay, right? But what is the benefit of this, of having this special form? Okay. To understand that, we will look at this special case of systems where our matrices are square matrices. Okay. So suppose we have a square matrix Rxi. All right. By the way, what is the rank of this system then? Can anyone tell me? You see, there are these 2 non-zero rows. This row is full 0. So the rank just like the ordinary understanding of rank is 2. It's a rank 2 system. Rank of this matrix is equal to 2. Okay. Rank here we will define as an outcome of this row operations, these unimodular row operations. At the end of the unimodular row operations, when we have the upper triangular structure, read off the number of non-zero rows. That's the rank of this system, of this matrix. Okay. Right. Now, suppose we have an R-Xi matrix, which is a square matrix. R-Xi matrix, which is a square matrix. By the way, as I said, I will be using this notation and this notation interchangeably. You can keep in mind that these two are the same, yeah, and it really is just a matter of convention, or a matter of style. Why? Because this means it's a matrix with entries coming from the polynomial. This means that it is a matrix polynomial, right? Like, for example, this polynomial that I wrote, the part of the polynomial matrix, say this one, yeah. Now, this is following this convention, but I can also write this matrix as xi cube times 0, 0, 0, 1 plus xi squared times 0, 0, 1, 0 plus xi times 1, 1, 1, 1 plus constant 1, 2, 1, 1, right? You see? So, this is like a polynomial, but coefficients are matrices. That's what this notation means, but they essentially are the same thing. Okay. Right. Now, where were we? Okay, this is a square matrix, a square polynomial matrix. Now, suppose I do some elementary or unimodular row operations. Row operations. And I bring this matrix to an upper triangular form, tilde xi so this is going to be R11 xi 0 okay, let me write R12 xi as well, R22 xi RGG xi. Okay. What is the determinant of this matrix? Determinant, of course, is the product of R I xi, I going from 1 to g. Right? Now, how is R tilde related with R? There exists a unimodular matrix U xi which multiplies R xi to give me R tilde xi. You agree? Of course, because how did we obtain our tilde xi? By doing elementary row operations. So, it's a series of elementary unimodular matrices. So, it's the product of those unimodular matrices, finitely many, and finite product of unimodular matrices, of course, is unimodular, right? Now, what is the determinant of this unimodular matrix? The determinant of this unimodular matrix is some non-zero constant k. So, non-zero constant k times the determinant of R xi is the determinant of R tilde xi then, but the determinant of R tilde xi is the product of all this 1 to j R I xi. Okay, great, no? So, now if I assume that the determinant of this guy is not 0, that means the determinant is not 0, some polynomial, then this polynomial must also be non-zero, and you know polynomials form what is known as an integral domain. Two non-zero polynomials when multiplied cannot give us a zero polynomial, cannot give us the zero polynomial. Product of non-zero polynomials is non-zero. Yeah. So, I mean it's 0 only if at least one of them is 0. So that means in order for this to be non-zero, in order for this to be true, each of these polynomials must be non-zero. What does that mean? Each of these polynomials being non-zero means these diagonal entries must be non-zero. Okay, these diagonal matrix must be non-zero, which means this is like a proper upper triangular shape. Now, what happens when we have an upper triangular shape? R1 1 psi, R1 2 psi, 0, R2 2 psi, 0, 0. I don't need that. I can use dot 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 0 0 RGG psi. Do you see what is happening here? If I want to solve for the simultaneous equations, simultaneous system of ordinary differential equations, I might as well solve this because the two are equivalent, the behaviors are equal. Remember, because of the kernel, because of the unimodular row operations, kernel of R psi is equal to kernel of, exactly equal to kernel of R tilde psi. So I might as well solve this system of equations instead of the more complicated one, that is this one. Instead of solving for R psi W equal to 0, I will solve this upper triangular system. Now what is the benefit of upper triangular system? Remember, the benefit, just like the benefit we have in solving linear equations, not differential, constant linear equations in linear algebra. If we have an upper triangular form, I mean the benefit that you have when you're having this, when you have done Gaussian elimination and obtained a row reduced echelon form. For the square case, what is the benefit? You can solve this last equation independent of the ones before, isn't it? Because you see, for the last equation, there is only Wg appearing, no other W's appear. So you can solve this scalar differential equation like a standalone differential equation. Okay? Now, let us assume that we know how to do that. We will see how to do it. But let's assume that we know how to solve that equation, and we can get a Wg, a particular Wg from the space of C infinity functions. For difference equations, you need to know how to solve difference equations, right? Single standalone difference equations. Now, once we have done that, once we have obtained a Wg, let me call that a Wg hat, particular Wg, for some initial condition for Wg, right? Somebody would have specified this initial condition, and we have solved this this standalone scalar difference equation to get this Wg hat. Once we have that, let us look at the equation immediately above that. What is it called? What is this process called in Gaussian elimination when you're solving linear system of equations, not difference equations, but just constant equations? This is called back substitution, right? Can we do back substitution here? Notice, what is this? We have R g minus 1 comma g minus 1 psi acting on W g minus 1 plus R g minus 1 comma g psi W g, and that is equal to 0. Back substitution would require that this is okay, Wg hat, what we have already solved, what we have already obtained. Now, you see, this is just a single input, single output kind of a situation. I mean, those of you who have done basic control courses, you just immediately realize that this is just like a differential equation with two variables. This is like an input which is given to us. This is like an output. Yeah? How do we solve for it? Well, we just solve for the homogeneous part. That is, we solve for Rg minus 1, g minus 1 psi acting on Wg minus 1 equal to 0. That will give me solutions coming from the initial conditions, right? right? And then I will have to obtain a particular solution for this input. How do I do that? Well, one way of doing it would be Wg minus 1, the Laplace transform of that must be equal to Laplace transform of, okay, just you know, I can just use the standard notation Rg minus 1 comma Gs divided by Rg minus 1 comma G minus 1 S Wg in the Laplace transform. Yeah? The Laplace transform of Wg hat. Yeah? But Laplace transform is not really correct here because you see we are looking at C infinity over full line. Laplace transform only starts from t equal to 0. But in any case, there are many ways of solving differential equations through this transformation kind of ideas, transform kind of ideas. But just to get the point through that I can solve for it, I just have to find out a particular solution, the so-called particular integral of this system, right? This is the transfer function corresponding to which I have to find out the particular integral for this particular input Wg hat. In other words, I can solve for it. This is once again back substitution, but a little more complicated. Just that, yeah, just that much. The philosophy remains the same. Yeah, just like in the constant linear equations case, you solve the last one first, and then you do back substitution. Here also we solve the first one, the last one first, and then do back substitution. But we have to be a little careful while doing this back substitution. We have to remember that we are actually solving differential equations, so we have to solve the homogeneous part and the particular integral part and so on, right? And now I'm sure you get the drift, what's going on. Now do back substitution again. So I have obtained, for the given initial condition, I have obtained a pair of such functions, Wg minus 1 hat and Wg hat. I will use these two to get Wg minus 2. Why? Because my third from the last equation reads g minus 2 xi acting on Wg minus 2 is equal to, or plus, that's the same thing, minus of R g minus 2 comma g minus 1 xi Wg minus 1 hat minus R g minus 2 comma g xi acting on Wg hat. This I know, I have to solve for this. First I solve the homogeneous part, then I solve the particular integral. Great, no? Fantastic. So just doing back substitution. Now the question remains as to how to get the solution of a standalone equation R xi w equal to 0. I'm sure you know it, but we'll just brush up your memory a little bit, and then we will move on to something more complicated. How do we solve for this, and how do we solve for something like yeah, these two cases. These were crucial to understand, to get the solution for this system of equations. So let me just repeat, let me just recap. So we are interested in knowing what happens to, how does one solve this equal to 0, right? Given system of ordinary differential equations, provided it's square and also determinant plus 1. First do this unimodular row operation and convert it to an upper triangular matrix, because the determinant is non-zero, these diagonal entries will be non-zero, right? Then just do back substitution. Just do back substitution. Solve the last one first and then keep on doing back substitutions. If we know how to solve this equation and how to solve this equation, we will know how to solve the system of equations, because it just involves steps where you need to solve something like this at each step while doing this back substitution, right? While trying to solve for this, while trying to understand this, we will also see how this ultimately leads to this very important question that we had already posed a couple of lectures back, that we have already seen that if there are two systems of equations having the same equation module, if the row spans are equal, then that implies the behaviors are also equal. What about the converse? Is this true? When is this true? When is this not? And it turns out that the answer will come via these efforts. This and many more is what we're going to see in the next few lectures. Till then, bye.